to give a talk. It's a pleasure to be at this wonderful place. So I will talk about the work, which is a joint paper with Sylvia Pufu and Ron Jacobi, which appeared 2 months ago. So the background for this talk was a paper by these people, Beam, Lemos, Leander, Pillars, Rastelli, and Van Ries, where they found the structure of chiral algebra in 4D n equals 2 and 6D n equals 2,0 theories, as well as other paper by Chester, Lee, Pufu, and Jacobi, and also by Beam, Pillars, and Rastelli, where they described the one-dimensional topological sector in three-dimensional superconformal field theories. And the goal was to get a better understanding of this 1D topological sector in 3D case. And, well, develop a tool to effectively compute its structure constants, because this is some 1D topological theory. It's described by a star product, which encodes correlation functions of the 3D n equals 4 SCFT. And the basic, well, and then in the process, it turned out that we can also generalize away from the CFT point. So, and the basic method is to put theory on S3 and then apply localization. So first, I will briefly review the old story about cohomological reduction in superconformal field theory, then tell you about the general n equals 4 theory on S3, which is a generalization of the SCFT story, and then describe specialized to Lagrangian theories built from vectors and hypers, then describe the localization and the properties of the 1D theory which we get, which is the gauged version of topological quantum mechanics, and then describe some applications, some examples. So so in 3D n equals 4 theories, the superconformal symmetry is described by this superalgebra, OSP4/4, or depending on notations, OSP4/2, depending on whether you like more complex numbers or quaternions. And it has SP4 or SO5 conformal subalgebra, and our symmetry is SO4, which has two SU2s, one SU2H, which will act on Higgs branch, and another SU2C, which will act on Coulomb branch, and then there are Q and S superchargers. Each of them has, each supercharge has, well, 3 indices. Let's say the first one is a spinor index, and then there are SU2H and SU2C index. Dot distinguishes SU2C index. So we can consider the following linear combinations of Q and S supercharges, where R is just the parameter which has dimension of length. They are nilpotent, and they anti-commute to this generator, where M12, so we forgot to say we work in the Euclidean space, and M12 is rotation in the plane x1, x2 plane. And then R bar is a generator, one of the generators of SU2C. And also, since there's radial quantization, there is a corresponding conjugation in radial quantization. And the anti-commutators of these superchargers with their conjugates, they give you dilatation minus another R symmetry. So we have these nilpotent superchargers, and I just copied this algebra. Okay, since they're nilpotent, let's consider their cohomology. They turn out to be isomorphic and also annihilated by this Z. And in particular by the geometric part of M12, which means that if you want to study cohomology of local operators, you can only insert them at the fixed points of M12. So M12 is a rotation in a 1-2 plane. Therefore, there is a fixed point at its origin. And so you can only insert local operators at the line parameterized by X3. And using the standard Hodge theory argument from this equation, you get that at the origin, these operators in the cohomology are just described by this equation, D equals R11. And there happen to be the Higgs branch chiral ring operators for the corresponding choice of Cartan of SU2H. Well, because when you describe chiral ring of n equals 4 theories, you have to first choose the n equals 2 subalgebra, which corresponds to picking Cartan generators in SU2H and SU2C. And with the proper choice of the Cartan generator of SU2H, you get that this is the condition satisfied by chiral ring operators, Higgs branch chiral ring. And another important fact is that if you consider such twisted translations, so P3, the ordinary translation in the X3 direction, and then you twist it by the R symmetry, what you get is a Q-exact operation. So you can use it to translate cohomology along the line, and there's no X3 dependence at the level of cohomology because this operator is Q-exact. So just to summarize, the local operators in the cohomology of this supercharge are given by the Higgs branch chiral ring operators, twisted, translated along the line. Another way to think about it is that you choose the choice of Cartan generator in SU2H changes once you move along the line. So you choose Cartan in the SU2H, and once you move along X3, this choice changes, and at every point, the operator in the cohomology is chiral with respect to that choice of Cartan. And since they are in the cohomology, and since the twisted translations are exact, Q-exact, the correlation functions are topological. In other words, they do not depend on insertion points, only on their ordering along X3. So you get some associative but non-commutative product on the Higgs branch, which is described by a certain star product, which we're going to compute. Yeah.
Could we just point again the first point? So you move along X3 and then you rotate what? The complex factor?
You can think this way as well.
So there's like the filters here and moving on the filters here, and that's sort of depends.
Yeah, yeah. There are like many different equivalent ways to think about it. And this is just an example. So if you have Q small here are scalars from the hypermultiplet. So if at the origin, if you choose Cartan such that Q1 is chiral, then the twisted translated field would be this, which is just Q1 plus X3 times Q2. More generally, if you have some Higgs branch operator with a lot of indices, you just contract it with this polarization U, and you get twisted translated operator. And since general Higgs branch operators, they're constructed as gaussian variant polynomials in the hypermultiplet scalars, and those that are polynomials in Q1 and Q1 tilde, they're chiral if you choose sigma 3 as the generator of Cartan subalgebra. Then twisted translated operators general two-set translated operators are just gauge invariant polynomials in this capital Q and Q tilde. And of course, there's also a mirror construction of supercharges QC, whose cohomology is related to Coulomb branch. And they would also give you corresponding non-commutative deformation of the Coulomb branch chiral ring. But here we'll focus on Higgs branch, because, well, Coulomb branch is part of ongoing research, and it's more complicated than Higgs branch. The localization part is more complicated. So that was a review of the old story. Now let us put this SCFT on the sphere. The sphere of radius r, where r is the same parameter which was before in the definition of those supercharges. Yeah, it's just a fun picture to illustrate that when you put theory on the sphere using stereographic projection, conformal and usual killing vectors, the get mixed with each other. Like, for example, if you consider two-dimensional sphere which touches the plane and you do stereographic projection, you can consider rotations of the sphere which fix the point where it touches the plane, and they correspond to isometers on the plane. But then there are also other isometers on the sphere which do not fix that point. And on the plane, they're not isometers anymore. They're actually conformal transformations. Like here, there's the linear combination of translations and special conformal transformations. So the whole point is to illustrate that when you put theory on the sphere using stereographic projection, usual isometers and conformal transformations, they mix with each other. And this has actually consequences. Namely, consider the following subalgebra of the conformal algebra: SU2/1 plus SU2/1. It is the choice of this subalgebra is parameterized by the choice of Cartan elements in SU2H and in SU2C, which we call H and H bar. So it has U1L plus U1R symmetry, which are just these Cartan generators. Then it also has the SU2L plus SU2R part, which is generated by transformations, just rotations, and these linear combinations of translations and conformal transformations. And there are then corresponding supercharges. So it turns out that our supercharges Q1H and Q1 and Q2H, as well as the corresponding Coulomb branch supercharges Q1C and Q2C, they belong to this subalgebra. And when you put theory on a sphere after stereographic projection, these SU2L and SU2R, they just become isometries of S3. Because as I explained, these conformal transformations on the plane, they correspond to isometries on the sphere. So from the point of view of the sphere, this algebra is actually just a supersymmetry algebra. It doesn't require conformal symmetry now. So from the S3 point of view, we just study n=4 theories with this algebra. And note that in the limit when radius of the sphere goes to infinity, this gives you the Superpoincaré on the flat space, this SU2/1 plus SU2/1. And now, since before local operators, they lived on the line, on the fixed line in space, after stereographic projection, they will live on the great circle inside of this, on this sphere. So it's also useful to combine these operators into such linear combinations depending on arbitrary parameter beta. And now QH beta is squares to this rotation with our symmetry, and we will study cohomology of QH beta in the equivariant sense. So it means that you have to restrict to Z invariant operators and study cohomology of QH beta on that subspace. And so the general setup now is that we have some n equals 4 theory on S3 with this superalgebra SU2/1 plus SU2/1. You pick supercharge, which squares to U1 isometry and the R symmetry. And note that it's not enough to simply take supercharge from SU2/1 left or SU2/1 right, because the isometries that would appear in the left algebra are just left invariant vector fields. They do not have any fixed points because, well, the group acts on itself transitively. So if you do localization with any of those supercharges, you cannot get any positive dimensional localization, quantum field theory. You simply get matrix model if you localize with respect to supercharge such that Q squared has no fixed points. And this would be the old localization by Kapustin, Willett, Yakov, if you pick supercharge from only one of the factors. But our supercharges, both the linear combination and each of them separately, they all are given by sums from something from the left and something from the right. And the fixed point set of this isometry, of U1 isometry, which is in Q squared, will be the great circle of S3. And we will insert local operators there. And again, there's a Coulomb branch analog for everything, but here we only study the Higgs branch case.
So is the star product commutative now? Because you can go around the circle?
No, still non-commutative.
Why is that?
You will see some, well, okay, the fields of this one-dimensional theory, they will be antiperiodic. And the analog of twisted, so yeah. For this story, it is useful to view sphere as a circle fibration over the disk with fibers shrinking at the boundary. And this is simply considering coordinates theta, phi, and tau, and with such a metric. So it's a usual thing. And then you think of theta as a radial coordinate of the disk, phi as an angular coordinate, and then tau just gives you a fiber, U1 fiber, over every point of this disk, except and it shrinks at the boundary, which is reflected by this cosine. So, and the U1 isometry, which appears in Q squared, is simply the tau rotation. So it just rotates fibers of this vibration. And so the fixed points are just the boundary of this disk where these fibers shrink. So yeah, and it's parametrized. The boundary of the disk is parametrized by phi. So the analog. Question?
Oh, how does this compare to the Hopf vibration?
Well, it's different from how, so. Okay, I see. So this, so the sphere is embedded in C2 like this, and then Z1 is, say, sine theta e to the I phi. Z2 is cosine theta e to the I tau. That's the definition of these coordinates. So Hopf circles correspond to rotating phi and tau together simultaneously by the same angle. So now the analog of those twisted translations that we had in flat space now are twisted rotations. When you so p phi is just the derivative with respect to phi, just the rotation in the phi direction. And now the Q exact combination is this, where RH and RC, they're related to generators of the R symmetry in this subalgebra this way. So SU2/1L plus SU2/1R. It has this U1L plus U1R R symmetry generated by RL and RR. And it's just, so now you have this, and this RH is also the same as the Cartan generator of SU2H. And as I already told you before, stereographic map matches twisted translated operators on the line to this twisted rotated operators on S1, where you move them using this P phi hat. And this is how these twisted rotated operators look on the sphere. Again, they're linear combinations of scalars from the hypermultiplets. And note that these linear combinations, they are anti-periodic on S1. And this is actually good because if you want to have something topological, say on the line, you would think that the two-point function should be something like the step function or the sine function. But if you put it on the sphere, on the circle, you cannot do it if you try to make them periodic. But here they are anti-periodic. So you don't have to deal with the zero mode on the circle. So, okay. So let us specialize to the class of theories that we're going to study on S3. Namely, these will be Lagrangian, just gauge theories constructed from vectors and hypers, vector multiplets in the adjoint of G, and hypermultiplets in the representation R. There's probably not the best idea to put action on the slides, but I still did it. So the action for hypers in flat space, it would be just invariant under the full OSP 4/4, and it is on the sphere. It is still invariant under the full conformal algebra, and it differs only by this curvature correction. And of course, there is the derivatives are covariant now. So this was just the hyper action, and also note that nothing. For vector multiplets, the action, so while for hypermultiplets, the action is invariant under the full OSP 4/4, for vector multiplets, it's now only invariant under the SU2/1 plus SU2/1, because it's not conformal. The G Young-Mills has dimension in 3D, and it has these curvature corrections, and it also explicitly depends on this H and H bar, which define how SU2/1 plus SU2/1 is embedded in the superconformal algebra. Of course, the action could be also written in terms of just multiplets of this algebra, but it is convenient to use this superconformal variables like phi a dot b dot, because then you can, going to conformal points simply corresponds to taking G Young-Mills to infinity. And supersymmetry transformations have the same form as for superconformal case. except that the parameters are restricted to be only those killing spinors which are preserved on the sphere. Okay, and we can also add Fi parameters. So while on the flat space you have triplet of Fi parameters, when you're on the sphere with this algebra, there's only one real Fi parameter. From the flat space point of view, if you want to compare, or say at the when you go, it's like turning on a linear combination of real and complex Fi parameters in the flat space theory. So there's only one Fi parameter here, and similarly, you can add masses by adding background vector multiplets that gauge the Cartan of some flavor symmetry. And again, there's only one mass parameter, one real number for every U1 flavor symmetry, which from the flat space point of view would correspond to turning on some linear combination of real and complex masses. And these masses and the Phi parameters, they simply centrally extend our supersymmetry algebra. So, which I can explain later if in more detail if anyone is interested. So one remark is that any SU2/1 plus SU2 subalgebra of our supersymmetry algebra, it's simply the standard n equals 2 algebra on S3. And from that point of view, the Young-Mills, the vector multiplet is just describes an n equals 2 vector multiplet plus an adjoint n equals 2 chiral of R charge 1. And then the action that we have for Young-Mills is just the standard Young-Mills n equals 2 Young-Mills action plus the action for a chiral multiplet of R charge 1. But the way we write it actually here makes connection with the SCFT variables more transparent. So now let's move to localization part. So we want to apply supersymmetric localization using this supercharge QH beta. So it means that we want to add a Q-exact term to the action. So like this QH of psi multiplied by some large parameter t. And this term has to be non-negative definite. It has its bosonic part has to be non-negative definite. The standard argument says that this does not affect the path integral with Q invariant insertions. And so by taking the limit t to infinity, the path integral localizes to the 0 locus of this localizing term. And so we call it the localization locus. It turns out that a very useful fact is true that this Young-Mills action is exact both to Q with respect to QH and with respect to QC. So it means that you can actually use the Young-Mills action itself to perform localization. And first, we localize vector multiplets using the Young-Mills action as a localizing term. It is known from the literature, and since I told you before that this S Young-Mills is simply the standard n equals 2 Young-Mills action plus the action for a chiral multiplet, it's just known that it's easy to see that it exact with respect to supercharges in any n equals 2 subalgebra of this n equals 4 on the sphere. And so to localize vector multiplets, we don't really need to do anything. We just can use known results, which were obtained by Kapustin, Willett, and Yakov. And after we do that, the vector multiplet, it becomes restricted to its localization locus, which is very simple. Everything vanishes, all the fields vanish, except for one component of the scalar, which is given by sigma, a constant matrix in the Cartan of the gauge group. And there are also auxiliary fields. They take these values proportional to sigma. And it's also known that the one-loop determinant for this vector multiplet localization is simply this, which is, again, derived by Kapustin, Willett, and Yakov. So now we have to deal with hypermultiplets, which are simply coupled to this background. So far, the answer we have looks like this. So there is this part which came from localization of vectors, 1 over the order of wild group, integral over the Cartan subalgebra, and this vector multiplet determinant. And then there's a remaining path integral over hypermultiplets, where capital calligraphic H denotes all fields of the hypermultiplet. And it's coupled to vector multiplets restricted to the localization locus. Already now we see that this action is actually Gaussian in hypermultiplet fields. So in principle, already using this, you can compute correlation functions of those twisted translated operators, simply using Wick theorem in this Gaussian action, and then all you have to do is perform the finite dimensional integral over the Cartan subalgebra. However, we can do even better and reduce this three-dimensional Gaussian theory to one-dimensional Gaussian theory, also coupled to this matrix sigma. And let me start by giving the answer. So here we have the same part corresponding to vector multiplets. And the hypermultiplet path integral is replaced by the one-dimensional theory, where Q and Q tilde are fields living in the circle. They are antiperiodic. And the action looks like this. Well, and Q lives in the representation R, which is the representation we use to of hypermultiplets. And Q tilde is in the adjoint, in the dual representation. So how do we show it? The simplest, the most naive proof is just check that this theory gives the same answers as the 3D theory on the previous slide. Both theories are Gaussian, so it's easy to check it. Just compare partition functions and compare correlation functions. And to compare correlation functions, you just need to compare Green's function. The only subtlety is that in this one-dimensional theory, you should be careful about choosing the integration cycle in the path integral. Well, because you need to make sure the path integral converges. In the usual sense used in the physics literature. But more conceptually, we can also perform localization of hypers in the background of sigma. The key steps would be, well, of course, solve VPS equations, where psi are fermions in the hypermultiplets. Those VPS equations imply, so there are two types of equations. They imply two things. One is that all fields are independent on this tau variable, where tau is the, well, if you remember, it's the coordinate along the U1 fiber when I think about S3 as a U1 vibration over the disk. So really, all fields can be reduced to just fields on the disk. And the remaining BPS equations, they're just certain partial differential equations on this disk. And solving them shows that the localization locus for hypermultiplets is parameterized by this single anti-periodic function on the circle.
When you solve it, you really have to choose a contour for your field.
Contour,
Or choose a reality.
yeah. So the fields in the three-dimensional theory, they satisfy standard reality conditions. So it's just that QA is this. And this is the same as this. And the BPS equations that hold on the disk, they actually, so if you introduce Q plus minus. Huh? The auxiliary fields, okay, there are two kinds of auxiliary fields. One in the vector multiplet, another which I haven't introduced yet, but I will that you introduced to close supersymmetry of shell on the hypers. They all satisfy also the standard. So the vector multiplets ones are, I mean, let's think about abelian theory. And the ones that I will introduce for hypers, they also satisfy the standard. But it's true that reality condition is very important because it also, BPS equations together with reality condition, they imply those partial differential equations on the disk.
But with this choice, the QFT factor is positive. This choice.
Yes. So the BPS equations, they just look. So if you have this variable, I call it Z1 here. Let's just call it Z. So, on the disk, they just Okay. Well, the whole point is that these equations can be solved, and they're determined by the value of fields at the boundary, and those completely encoded in this one, in this anti-periodic function. And then Q tilde is related to Q through a reality condition, which follows from reality of fields of original theory and those BPS equations. So this integral goes over the trivial middle dimensional integration cycle in the space of complex fields Q and Q tilde. And this is what happens to the classical action. So first, since fields are independent on tau, the action on the sphere reduces to the action on the disk. And then it turns out to be a total derivative on the disk. And so it just reduces to the action on the boundary of the disk. So another key step is to construct a localizing term, which will do the job, so which will actually restrict to this locus, and will have no bad properties like flat direction for fermions or anything. And to compute the one-loop determinant, or in our case, to prove that this determinant is actually equal to 1. I'm not going. So the construction of good localizing term is a bit technical, so I will not go into details. The reason is that well, there are certain difficulties. They're related to the fact that a lot of things, a lot of expressions degenerate at the boundary of the disk. And whereas in the standard localization computations, the operators that you deal with are usually transversally elliptic, here they are not transversally elliptic. And so you actually have to approach it more directly by studying the spectrum. And the upshot, which I can tell in person to whoever is interested after the talk, is that there are no flat directions, and then the determinant of that produced by that localizing action is just 1. And again, there is a shortcut to the statement that the determinant is 1, which is just to compute the partition function and check that the determinant is actually 1, because the theory before and after localization is just Gaussian theory. Okay, seems like I forgot to mention that I also have to, that this supercharge has to be closed off shell in order for the localization to work. And you cannot close the whole supersymmetry algebra on off shell on hypermultiplets, but you can close this one particular supercharge. Actually, you can close a subalgebra by adding auxiliary fields. And this was used in all localization computations, and I think it originates from the work of Berkovitz, where he described how to close subalgebra off shell. So now let me also describe this contour of integration. So our fields, they are, as I told you, they are anti-periodic on the circle. So the Fourier expansion goes over the half-integral modes. And the integration cycle should be of this form. It's Cn, that Cn tilde is related to Cn complex conjugate, plus there is some phase in front, chosen in such a way that the path integral converges. All you have to do is plug it in that 1D action and see that the real part is positive definite. And the particular contour which follows from this localization computation has the following little complicated form. This phase is given by this expression where I is the modified Bessel function, the one which is regular at 0. But of course, you can deform contour whichever way you like once you preserve the convergence of path integral. And in particular, it can be taken to have the following simple form, which, it incidentally is just the sigma to 0 limit of this expression, of this phase, is given by this I times sine of n. This contour can also be obtained using the Morse theory, as was done in Within's paper from 2010 on quantum mechanics. And the cycle he had is very similar to the cycle we have, basically the same one up to the difference that our fields are anti-periodic on the circle. So it's just a fun fact that what we get is an interesting realization of analytically continued quantum mechanics, but as a sector in the supersymmetric theory. Well, now let me talk more about properties of this 1D theory that we get. I'll just write its action one more time here to have it. So far, it's just the Gaussian theory with fields Q and Q tilde coupled to a matrix model with sigma being the matrix in the Cartan of the gauge group. In fact, we can reinterpret this as a one-dimensional gauge theory. The factor that we had, so we had this integral over sigma, then there was this determinant over adjoint, where prime denotes that you omit zero weight from the determinant. And then this determinant can be actually reinterpreted as a Fadeev-Popov determinant, which appears in gauge fixing of this action. So the gauge condition is simply that d phi of a phi is 0, right? And then it's this gauge condition is solved by the following expression, where sigma is a constant. And this gauge fixing precisely gives what we got, or what we obtained by localization. So this is a very useful interpretation, but there is one subtlety that we don't have I here. And this is not just because there are different conventions. The group element is either exponent of the algebra, of the element of the algebra, or I, or exponent of I times the algebra. Here we use the convention where group element is e to the I times the algebra element. The absence of I here means that actually this quantum mechanics is analytically continued. And this requires some further understanding, but I take it more like not as a problem, but as an exercise which has to be done in a finite amount of time to describe precisely precisely the contour in this theory, which justifies this analytic continuation. Assuming that it exists, this interpretation tells you that, first of all, the theory is topological, because there is no metric on the circle involved. And this means that correlation functions of gauge invariant operators are topological, so they do not depend on insertion points. But it's only true for gauge invariant operators, of course. And this one-dimensional gauge field, it acts as a Lagrange multiplier which imposes the constraint, this constraint in the Higgs branch chiral ring. Well, in particular, it means that composite operators which involve this combination, they should also be trivial. And with the proper definition of composite operators, they should be just 0. Well, if you define composite operators by taking two operators and moving them to each other. But of course, there is freedom. Now we can also add masses and phi parameters, and they deform 3D theory away from the conformal point. And they are they're reflected in the 1D theory. Turning on masses just corresponds to shifting this sigma by the mass matrix. It just, when you write this expression, should keep in mind that sigma acts on gauge indices and m would act on flavor indices. But formally, you just shift it like that. And in the 1D gauge theory, it's just shifting the connection. Now, Fi parameters, they simply correspond to adding such a term in the 1D action. And from the gauge theory point of view, it's just the 1D analog of the Chern-Simons. Again, it's analytically continued, because if you look carefully, go back to Minkowski's signature and look carefully for all factors of I, you see that this I, normally it wouldn't be there in the Chern-Simons action. And also the coefficient of the Chern-Simons action would be quantized. Whereas, when you analytically continue, the imaginary part of Chern-Simons level, it doesn't have to be quantized. So really, Fi parameters, they correspond to such analytically continued Chern-Simons term. Well, the whole 1D theory, as I told before, is analytically continued. Now, okay. By the way, how much time do I have? 10? Okay. Correlation functions of the twisted Higgs branch operators, they are still topological in the presence of Fi terms. And the reason is that by the way, does everyone see when I write here? Okay. So there was this relation that Q H of something was twisted rotation. And in the presence of Fi parameters and masses, you also get a central charge here on the right, actually. So for those operators that have non-trivial central charge, such twisted rotations, they're not Q-exact anymore. So operators with non-zero central charge, their correlation functions have some simple fixed by non-trivial dependence on coordinates of insertion points. And for operators, for Higgs branch operators, they receive non-zero central charges if you turn on mass parameters. For Coulomb branch operators, they receive non-zero central charges if you turn on Fi parameters. So turning on Fi parameters on the Higgs branch doesn't introduce central charge here. And so the correlation functions are still topological. But these Fi parameters, they, of course, deform the OP in this 1D theory. No, this is what I just explained. So, well, but when you turn on masses, the correlation functions of these Higgs branch operators, they become position dependent. And as the 3D theory flows from the UV to the IR, this 1D theory interpolates between the topological limits as this mass goes to infinity. So in the remaining time, I will describe one example. So we have this very simple 1D Gaussian theory, which gives exact answers for certain types of correlation functions in 3D n = 4. In particular, it computes n-point functions of twisted Higgs branch operators, where you have arbitrary number of operators all inserted at the great circle. And it also captures 2- and 3-point functions of arbitrary Higgs branch operators for superconformal theories. Because, well, because of conformal invariance and R-symmetry in the SCFT case. Because if you have 2-point function, then you can always find the great circle which passes through these 2 operators. And since this twisting corresponds to taking linear combination of various R-symmetry components, just using R-symmetry, you can relate 2-point function of arbitrary Higgs branch operators to the 2-point function of these twisted operators. And this is the same for 3-point functions, except that using conformal symmetry, you can always put the 3 points on the great circle. So essentially, you find the whole CFT data for this sector of this theory. And it's encoded in a certain star product on the Higgs branch. So the example I want to consider is SQED with n flavors. So it's just a U1 gauge theory, which has n hypermultiplets of charges 1. Then these fields of the 1D theory are Q and Q tilde. Q has charge +1, Q tilde charge -1. Yeah, so it's a very simple theory. Then this combination Q tilde I, Qi, where it's summed over I, it vanishes under the correlators. And so the resulting algebra is generated by traceless bilinears like this. And they're also nilpotent, obeying this equation. So it's a known fact that the Higgs branch is given by minimal nilpotent orbit for the flavor group SUN. And then the rest of operators, the other linear independent operators, are just such traceless products. Where, of course, you should be careful about defining composite operators, etc. If you just package all these tensors into one structure by taking sum with the SUN polarization vector, and moreover then also package them together like this, you can find that the 2-point function in this case, well, it's just to illustrate that it's calculable, and the 3-point function, and then identify the answer as a certain higher spin algebra. And you can also find the star product of these generators. And this is the full answer. So in this problem, the star product is actually described by what is called equivariant deformation quantization. So you can assign a weight. So if you assign weight 1 to J, well, it actually has conformal weight 1, and you assign weight -1 to L, or weight 1 to 1 over L, which is the deformation parameter, then you can see that you cannot go beyond the order 1 over L squared. So this is really the full answer. And if you turn on Fi parameters, well, all this computation can also be done in a similar way. It's just that the formulas get deformed by this Fi parameter. You still can find the star product, which now explicitly involves this deformation by a Fi parameter. And in the limit, notice that in the limit where L goes to infinity, this reduces to the ordinary commutative product on the deformed Higgs branch chiral ring, which is described by this equation, the deformed Higgs branch. And these relations, they identify, again, the algebra in the presence of Fi parameters as another known high-spin algebra.
You see Higgs spin algebra, you mean the result of reduction? You see Higgs spin algebra, you mean the result of reduction?
Say again?
When you call it the Higgs spin algebra, you see the result of reduction?
Oh, I'm really what I really mean is that what I really mean is that there's a paper by these two people where they classify high-spin algebras.
Is it the same as compared to you?
I don't know. So I'm not an expert on high-spin algebras, but it's just always fun to.
Very good in Higgs spin algebra is just a finite algebra. And one of the also derivatives, so there are operators and the derivatives, so it's just a quantization of the Higgs branch.
Yes.
So it's just finite algebra.
You mean this?
This Higgs spin is being called Higgs spin algebra.
Well, it's finitely generated, but it's not finite.
Do they call it a Higgs spin algebra?
Okay, they describe them as symmetries of a representation, so of a certain representation of SLN, and that's what they define. Yeah, I'm not aware of any more deeper connection, except that it's just the same algebra as described by those people. So that's it. Basically, there are some further examples that can be found in the paper, like a node quiver, which is a mirror of the SQED, in which case you can also describe this star product on the Higgs branch, etc. In that case, the Higgs branch is this Kleinian singularity, which in the presence of Fi parameters is deformed in a known way. Another example that can be found there is the U2 gauge theory with joint and with fundamental hypers. Yeah. So let me conclude. So what we found that well, there's also another remark that localizing with a Coulomb branch supercharge, we can also obtain partial results for the Coulomb branch. Since Yang-Mills action is Q exact, you can compute correlation functions of chiral operators, which are scalars in the vector multiplet. Unfortunately, results for monopoles are not available yet. Yeah, doing this, for example, for SQED, you can compare results with n-node quiver, and like it's a very naive test of mirror symmetry, in particular that the scalar of the SQED, the vector multiplet scale that corresponds to this Z in unknown quiver, which is basically Q tilde Q. And then there's work in progress to include monopole operators, in which case one has to be careful about boundary terms that are used to define, because you define monopole operators as defects, so you cut out a small hole and you need to impose some boundary conditions and boundary terms which would fix supersymmetry, to preserve supersymmetry, and to compute determinants in the monopole background. And there are more further possible directions, which are to generalize this to actions with twisted vectors and twisted hypers in order to study Chern-Simons, to add Chern-Simons terms. Include line and surface operators possibly, and of course the 4D n equals 2 case, which will be more interesting. And that's it.
Not question.